Hello everyone, my name is Fabian Ibarra, working alongside Charles Johnson and Matthew Kinney. Here for Mechanical Measurements, we're presenting our final project, the eddy current tachometer.
Johnson here. I'm going to give a brief overview of how the eddy currents work in our eddy current tachometer. First, we have a permanent magnet that's connected directly to a shaft. As that shaft rotates, the magnet spins along with it, creating a constantly changing magnetic field in its vicinity. Positioned very closely to the spinning magnet is a non-magnetic but electrically conductive disc that's made of aluminum. This disc is not directly connected to the rotating shaft. Instead, it is attached to a spindle that is restrained by a spiral spring and connected to our indicator pointer. As the permanent magnet rotates, its moving magnetic field passes through the stationary conductive disc. According to Faraday's law of induction, this changing magnetic flux induces a circulating electrical current, known as an eddy current. In accordance with Lenz's law, the induced eddy current produces its own magnetic field, which opposes the original magnetic field that created them. This interaction results in a torque or drag and will attempt to rotate the disc and its indicator in the same direction as the rotating magnet. As the induced torque causes the disc and its attached pointer to rotate, the pointer will move across the calibrated dial. The faster that the original shaft and magnet spins, the stronger the induced eddy currents and the greater their magnetic force, and thus the more the pointer deflects. Eventually, the system will reach an equilibrium point where the electromagnetic torque generated by the eddy currents is perfectly balanced by the mechanical resistance of the spiral spring. The position of the pointer at this equilibrium directly corresponds to the rotational speed of the shaft, which then is read in RPMs. For this project, there were 6 main design requirements. The first one is that the rotating shaft was controllable and stable for at least 10 seconds at a requested speed, and for a demonstration it was requested that we show 2 different speeds of our choosing. The measurement must either use a fly ball or eddy current tachometer to measure the rotational speed of the shaft. Number 3, the speed needed to be displayed with both a mechanical indicator and a digital readout. It could not be a console panel-based readout, something that you would see directly from programming such as Arduino, but an actual digital OLED screen. Number 4, the final product must be calibrated to give an accurate RPM, either using a stopwatch or a laser tachometer. Number 5, the budget must not exceed $105 to include microcontrollers, your displays, actuators, bearings, magnets, any miscellaneous hardware. This excluded 3D printing and any free materials, with the exception that if you used a reclaim motor or some other reclaimed hardware, you did have to include that reduced price in. And number 6 for the timeline, it must be demonstrated on December 3rd for our measurements class in 2025.
The way we powered our driven side of the eddy current tachometer was through the use of a brushed motor. We opted to use a Holmes Hobbies TorqueMaster Expert 540 brushed electric motor at a 35-turn coil winding. The reason for this was because it had a theoretical maximum RPM of 11,000, and we felt it suitable for our working RPM range, or our desired RPM range of our eddy current tachometer. Now, from here, there was a power shaft connected to it. This power shaft was connected via a flexible shaft coupler that was reduced from its 5mm bore to suit the motor's outboard 3.14mm bore. The shaft was then connected via the coupler and connected to the eddy current magnet holder. To power the motor, we used an electronic speed control, more commonly referred to as an ESC. The speed control we chose was the Hobbywing Quick Run WP 1080G2 brushed ESC. This had a continuous output of close to 80 amps, and it had an input voltage of 7.4 to 11.1 volts, and this was deemed necessary due to the fact that our power supply was going to be a 7.4 volt lithium polymer battery. We opted for using a LiPo battery versus a lead acid battery due to its ease of use, ease of implementation, and overall ease of transportation. With the very small footprint, it deemed as the most viable and suitable option for the application. To control the ESC, we used a standard remote control typically found in remote-controlled cars, remote-controlled planes, and other things of the sort. To actually produce the eddy currents, a 3D printed disc was modeled in SolidWorks and printed via Bamboo Labs A1 3D printer. The disc itself was made out of PLA material, and the orientation of the magnets altered between north and south. This was due to the fact that as the disc spins, depending on the input RPM, it produces an eddy current effect due to the opposing north and south poles of the magnets. With the eddy current disc only being 2 inches, it limited us to the size of magnets we could use. The magnets that were used were standard neodymium magnets that measured at a total of 8 millimeters in diameter, along with 2 millimeters in thickness. On the non-powered end of the eddy current setup, there was a 2-inch aluminum disc that was supported by a 2-inch aluminum disc holder that we 3D printed again out of PLA material. These were all supported by shaft carriers, which had a 5x10 by 4 millimeter bearing inserted into them to allow for free rotation of the driven and driver shaft. To mechanically display RPM, a Mach tachometer was assembled. The Mach tachometer had a few key features and components. The first being a mechanical stop as to where the needle would rest. This just included using a M4 by 12 millimeter cap screw with a nut on the back. Then the dial face had several markings on it, not shown in this image here, but in the real model, we had labels that were labeled at different set points in terms of RPM versus the amount of torque applied on the system. To prevent the complete rotation of the needle from one end to the other, if there were no restrictions, the needle would just spin freely, we used a hairspring. This hairspring was a hobby hairspring with an overall height of 1.6 inches, and this was connected to the input shaft from the eddy current driver, and here is the only restriction of rotation that was found in the system.
So one of the design requirements was the budget not coming in at over $105. So the way we reduced our costs is doing a lot of 3D printing for parts that would normally be machined. So you can see the plastic rotor for the aluminum disc and the plastic magnet holder that were both 3D printed. And then down at the bottom, you can also see the towers that were also 3D printed, which normally would have been made of some type of sheet metal. We were able to repurpose an RC brushed motor to save on costs, and then to eliminate like an AC to DC converter, which usually have a transformer and can be expensive. We used a battery to supply external power, which has the benefit of also not needing to be connected to the wall, so the setup is more portable. And then, yeah, so our total came in at about $83.16, about $20 below the budget requirement. So in order to stay on track and complete our design by the required test date, we had our first conceptual design overview on November 5th. This is where we presented our initial concepts for design and got feedback from our instructor on various things that we should implement or change before the actual physical project demonstration. Then we demonstrated the product working on December 3rd, and then our final report/presentation was set to be due December 13th.
Here we see a digital representation of our physical model. Here we can see the electric motor powering the shaft connected to the motor via a flexible coupling with 2 set screws on top and 2 set screws on the bottom, securing it in place, preventing any slippage. We then see the eddy current interface. Here we have the eddy current disc with the magnets in opposing polarities, along with the 2-inch aluminum disc, a non-ferrous metal. We then connected it to the dial face, or rather our tachometer, and here we could see where the clock spring is attached, along with how it is stopped with the nut through the back of it, and a drilled slot was made inside of the second shaft to prevent any slippage from the clock spring to the interface.
So here we can see our experimental setup. You can see us now driving the motor at our specified RPM. Now you can see the rotating disc and how it moves, and there is a gap there. You can see the mechanical gauge working, moving back and forth. And then we're going to go back and just to make sure. And then now we can see the RPM readout on the display that's constantly updating through the microcontroller. And that's just a brief overview of our demonstration. And then this is our experimental setup, so you can see the battery, and then we now have our 3D printed enclosure that houses all the electronics and keeps the dust away and minor water splashes. You can see the full setup mounted to the wood base plate that keeps everything stable. And then to the right you can see inside the electronics box where we housed the I2C module screen and the microcontroller, and then you can also see the breadboard that has the voltage divider and RC filtering circuits on it. So this is the experimental setup. As far as the evaluation and calibration, we performed an initial calibration based on the manufacturer's RPM ratings per volt that the motor was receiving, so we're able to base that off of our initial voltage divider circuit. And then to improve the calibration, since the RPM value from the manufacturer is not super reliable, we did use the digital tachometer and a reflective tape strip, and we were able to find several data points, and then these data points, at least 4, were mapped against a linear curve fit, and then a residual was performed on that. The values look okay, they fit a linear trend, and then so the code has calibration coefficients that we can modify, and that allows us to change the display output to an accurate reading. And then we can also use the RPM calibration to set the mechanical gauge limits, so we would add notches or marks where specific RPMs lined up on the mechanical gauge. So we used 5 subdivisions and with 4 marks.
Hi, Johnson here again. So, in conclusion, we did meet 5 of our design requirements and partially the 6th design requirement. So we were able to produce a rotating shaft that was controllable and stable for at least 10 seconds at that requested speed. We did implement the eddy current tachometer. We were able to implement both a mechanical indicator using our spiral spring and pointer, and then we used an OLED to give a digital readout of the RPM. We did not exceed our budget, coming in at $85, and we were able to demonstrate its function on the requested date. The only design requirement that we partially met was that calibration. So unfortunately, due to some of our materials, basically the 3D printed materials and the laser tachometer, the laser tachometer did not want to read the little makeshift reflective strip that we had made for it. That is something that needed like an actual reflective strip and not just a little piece of white paper or a black line. We had done some calibration based off the manufacturer and the general idea of how many volts of input to the motor would lead to a certain shaft speed. However, that doesn't always account for, some of the other frictional forces of additional bearings and things like that. So it generally was in the ballpark, but it wasn't like something that we can definitively say, hey, this is exactly what this RPM is. Of course, with all things, it really depends on the resolution that's needed. So if this was something that, we only needed a resolution of plus or minus 50 to 100 RPM, this tachometer definitely would have been able to do that. If we needed something that was down to 1 RPM, we would have had to have come up with a better way to fit that either reflective material or making a better mark so the laser tachometer would better read the discs that contain the permanent magnets. So all in all, we did demonstrate something that works. However, the calibration was something that needs improvement. And in the future, with the 3D printed material, would definitely include potentially a little strip of metal or something, maybe some aluminized tape to be a more reflective surface to give a better calibration. Thank you.